All right. Hello, everyone. I thought that I can do a couple of extra example problem. The one example problem that we did for the natural response of an RLC circuit, RL circuit, not RLC, RL circuit, had a current source in it, and since maybe this is one of the very basic lectures, some of you were struggling with having problems with the voltage source. So I thought that maybe I can do a couple of examples to include a voltage source as well. So hopefully this should provide some extra clarifications on how to solve these circuits. Okay, so let's think about this example problem here. In the circuit over here, we have inductor, right? And at time t is less than 0, we were connected at a switch at position A, and then at time t equals to 0, the switch is moved from position A to position B. Okay. So at time A, you have a voltage source in the circuit, and at time B, this voltage source was taken out. So that is why we are looking at the natural response. So we have to solve for all of these problems. And if you remember, right, here is a natural response current equation that we derived in the past. All right, so let's very quickly do this thing. So the very first thing it is asking to determine the initial current in the inductor. Right, so okay, so it is asking for finding the initial current in the inductor, right? Initial current is practically you have to find I naught. And how to find I naught? You can draw the circuit for t is less than 0. So t is less than 0, the switch will be at position A. In that case, you will get this, and rather than an inductor, I'm going to talk about inductor in a second. So 60 volts, you have 30 ohms, you have 90 ohms. Okay, so since the switch was at position A, we are going to assume that sufficient or some time has passed that the steady state was reached. And we know that in steady state, right, at steady state, inductor becomes a short circuit. So this is going to become a short circuit, right? So essentially all I have to do is to find the value of the I naught over here, right? So I naught is going to become, you have V over R, 30 plus 90, 60 over 120, you get 0.5 amperes. So this is the value of I naught. Let's do part B. Part B is find the time constant of the circuit. In order to find the time constant, right, so tau equals L over R. Let's redraw the circuit. Again, we find the time constant after the switching event. So this is how the circuit is going to look like after the switching event. So we have 70 ohms here, 90 ohms here, and 0.32 Henry here. So tau equals L, 0.32 divided by R, 70 plus 90, R equivalent essentially, right, which comes out to be 160. So it is going to come out to be 2 millisecond. So this is the value of the tau. This is the value of the tau that we get. So let's do the step number, the part number 3 or C. We have to find the expressions for I, V1 and V2 for tau is greater than or equal to 0. And again, this was a circuit for greater or equal to 0 at position B, right? So we are going to take the circuit into consideration now. And essentially the V1 is across inductor, V2 is across 70 ohms resistor, and current is flowing here, I. Okay, so I'm going to start with finding the current value of the inductor current I that is flowing through the circuit, through this RL circuit. And again, we can use this equation, I of t equals I naught e raised to power minus t over tau. So let's find the value of the C. I of t equals I naught e raised to power minus t over tau, right? And again, this is for t is greater or equals to 0. I naught is, what is the value of the I naught? 0.5 amperes, and tau is 2 millisecond. So I naught is 0.5 milliamperes minus tau is 2 millisecond. I can further rewrite it as 0.5 times e raised to power minus 500 t amperes. So this is a expression for I of t. Now we also have to find the expressions for v1 and v2 of t. So let's find the expression for v1 of t. Again, v1 of t is across the inductor. Okay, and we know that the voltage across the inductor equals L di by dt. So I'm gonna put the value of the L, which was 0.32 Henry. 0.32 times di by dt, and if I will take a differential of 0.5 e raised to power minus 500 t, so I get 0.32 times 0.5 times 500 e raised to power minus 500 t. Okay, so, and of course this should be minus 500. Okay, and if you were to solve this, it is going to come out to be minus 80 e raised to power minus 500 t volts. And again, this is only valid for 0 positive, as we discussed in the past. Okay, so this is v1 of t, right? Let's find, going back, we also need to find v2 of t. What is v2? v2 is the voltage across this resistor. So the voltage across the resistor is practically the current and the resistance. So we're going to do IR. v2 of t is I times R. So I is 0.5 e raised to power minus 500 t times resistance. Resistance was 70 ohms. Resistance is 70 ohms, so 70 times 0.5 is 35. So v2 of t comes out to be 35 e raised to power minus 500 t volts. Okay, and this is again for 0 positive. Okay, so we did that as well. The last thing is, we are interested in what percentage of the energy stored in the inductor is dissipated in a 90 ohms resistor. So practically what we want to find is how much energy was, how much percentage of the energy is dissipated in the 90 ohms resistor. Again, due to this excitation source before the switching event, some energy was stored in the inductor. So first we have to find the total energy that is stored in the inductor. Once we do that, then that energy will be released in this natural response in both of these resistances, 70 ohms and 90 ohms. And then we have to find the energy that is released or dissipated in a 90 ohms resistor, and then we're going to find what was that percentage. So let's do the D part. D part is, again, let's find out what's the total amount of the energy stored in the inductor at time t equals to 0, again before the switching event or right at the switching event, right? So we know that half Li square, so W0 equals half L I naught square, so we get half L is 0.32 Henry times I naught is 0.5 ampere square. So the value of the W naught that we got is 40 millijoules. Okay, so this is the total amount of the energy that was stored in the inductor. Now we have to find out how much of the energy was released in the 90 ohms resistor. Okay, so in a 90 ohms resistor, how much of the energy was released? So let's find the expression, and then we are interested in how much it is released in 1 millisecond or dissipated in 1 millisecond, right? Okay, not release, right? Resistor is going to dissipate that energy. Inductor is going to release the energy. Okay. So we're going to find an expression for time t, then we're going to replace 1 millisecond in t. So we are finding from 0 to t. 0 is the switching event all the way to time t, right? So for example, you can, do I square r times dt. So I square is Here's the equation of IFT. 0.5 square is comes out to be 0 to t. Let's write down the value for r. Is again, we are looking at the 90 ohms, and then let's find the value of I square. 0.5 square is 0.25. E raised to power minus 500t is going to become e raised to power minus 1000t times dt. Of course, we can change the variable of integration if needed as well. So let's solve this exponent now very quickly. Okay, so if we were to solve this exponent 0 to t, so 0 to t, 90 times 0.25 equals 22.5 e raised to power minus 1000 t times dt. Then it comes out to be 22.5 and 1 over, right? So if you were to take a differential, so first you're going to get minus 1 over 1000 minus 1 over 1000 times e raised to power minus 1000 t 0 to t. So you will get 22.5 divided by 1000 minus here e raised to power minus 1000 t minus 1, right? So what I'm going to do is I'm going to take this negative sign over here. So I would get 22.5 divided by 1000, 1 minus e raised to power minus 1000 t, right? So this will become 22.5. So this will become to 22.5 times 1 minus e raised to power minus 1000 t millijoules. Again, this 1000 becomes millijoules. So this was 0 to t. So if I were to do it at 1 millisecond, I will get, I'm going to essentially replace t equals 1 millisecond in the equation. And if I were to replace 1 millisecond, I will get 22.5, 1 minus e raised to power 0.0001 0.001 times t times 1000. I replaced the t earlier, right? And this should come out to be both of them can practically be cancelled, and this should come out to be minus 1. So 22.5, 1 minus e raised to power minus 1. So this is going to come out to be 14.22 millijoules. Okay, so this is the amount of the energy that got dissipated in the resistor. This was the total amount of the energy that was available, 40 millijoules. So practically you just have to find the percentage of energy dissipated in 90 ohms resistor for 1 millisecond was equals to 14.22 millijoules divided by 40 times 100 comes out to be 35.6%. Okay, so this is like one of the examples that we did.